Okay, welcome back everyone. So today I'm going to do a video on directional derivatives, and that's because it's going to lead up to a video that I'm going to do soon, which is on kind of a more rigorous foundation for Lagrange multipliers, and a really nice example that comes with it, but mostly for the more rigorous definition of structure for Lagrange multipliers. So let's begin by kind of getting the idea of what directional derivatives are. Basically, what directional derivatives are in words is essentially just how some function, for example, you can see this function here, is just some arbitrary function. It's how it changes in any direction. So, as we saw with partial derivatives, so partial derivatives with respect to x and with respect to the independent variables, those gave us the rate of change whenever we took a plane and sliced it along along some along the function, such that that plane is parallel to the independent variable that is being taken the partial derivative with respect to. And the same idea applies to any direction. We're essentially also taking a plane that's parallel to the vector. In fact, it's going to be unit vector that that we want to take the directional derivative with respect to. So let's just draw this out. So let's say we have our vector u hat equals a and ab, and we want to take the directional derivative with respect to u hat. And that would just mean, again, slicing a plane through a function as such. So, and at any point along this plane, where we can get, we'll get the instantaneous rate of change at the function. Okay, well, let's kind of see how we might calculate this, okay? And there are kind of two ways to see how to calculate this. So let's begin with the first way. And that way is to first consider this line that this u hat is kind of on the xy plane. So I'm going to kind of draw it out here. And I'm actually going to draw out the xy plane here, just to get a clearer idea of what this line is. So it's going to be something like that. So x, y. And we kind of want to define this line by some vector function r of t. So we have some vector function r of t. Actually, we use s. And the reason we use s is because we think of s as kind of arc length. In this case, it's kind of just distance. So we're parameterizing in terms of distance. And a property that we want this to have is that dr ds is equal to u hat. Because if we take at some point, if we draw out our r at any given point in terms of s, and then we have some, and then we add some plus dr, so infinitesimally small dr, so dr plus r, then notice that, well, this distance, we're going to travel some ds, some change in distance results in a change in r, so dr. So therefore, if we want to subtract dr plus r minus r, we're going to get u hat ds. The reason this u hat is here is because it has unit length, and we need this to be a vector. So that implies that dr equals u hat ds, which tells us that dr ds equals u hat. Okay? So this will be useful in our final equation. Okay, so let's quickly continue. And actually, this is not necessarily a necessity to do. In fact, there's another way to see this, which I'll show in a second. But now we're kind of ready to see this play out. So again, reiterating in a way what we just said about what the directional derivatives are. It's kind of the resulting. Now, just to get an idea of what this is, the notation for a directional derivative is going to be, for a function f, is df ds in the direction of u, which can also be written as, and I prefer this notation a bit better. It's a bit less clunky. It's this notation. So f(x, y). Okay, so these are this is the notation. It's the change in f here along some infinitesimal distance, right, at some point. So it's kind of the slope of this line at some point, x naught, y naught, right? And that's the idea with this notation. It's the change in f in the direction of u hat. So this is what we're trying to find, df ds, okay, in the direction of u hat. So in other words, if we want to calculate df ds, we can just use the multivariable chain rule. And that's just going to be equal to, well, all the multivariable chain rule is df partial f partial x dx ds plus partial f partial y dy ds. But notice that this is just going to be the dot product with the gradient of f. So and what exactly is this? Well, this is just going to be the derivative of our vector function, r of t. So that's going to be dr ds, which is equal to finally the gradient of f dotted with u hat. So that's it. And now another way of seeing this, perhaps a bit less, it's kind of a bit more concrete than kind of saying that this is dr ds. I prefer this method. Is noticing that this line can be parametrized with respect to distance as x of s equals, and y of s, obviously, equals, so at some initial point x naught, y naught, x naught plus, and then our slope, well, our slope is given by our u hat, and we're just going to get, for our x, we're just going to get a, or I should say, yeah, as. And then for y, we're going to get y naught plus bs. Okay? And then if we take the derivatives of these, look what we get here. If we take the derivative of this, we get a. If we take the derivative of this, we get b. And thus we just get our ab, which is our original u. So that's another way of getting this. Okay, now I'm going to show an alternative way of getting this here. So I'm going to completely wipe the board out, and this will finish this video, this final little proof. It's kind of a strange proof because it originates from a somewhat arbitrary composition, but you'll see that it actually works out very nicely. So first we kind of need to get the definition of what a directional derivative is. So at some point, x naught, y naught. Okay. So again, we have the slope. And first we'll think on a non-infinitesimal scale. So how would we find the slope between 2 points here? So, and then again, we still have our vector u hat, okay, equals a, b, and then we get to some other point, x naught plus h a, y naught plus hb. So you can kind of think of this as a specific point on our parametrized line in terms of s. So we're jumping to this point on our line. which is going to be some adding to the coordinates here, some HA and then HB here. Okay, and again, this is on the line. So how do we find the rate of change here between these 2 points inflicted on the graph of f? So to do that, well, it's going to be rise over run. This run here, well, it's pretty easy to see that. I'll kind of let you try that out, but it's pretty easy to see that it's going to be h. Okay, so we're going to have, well, our rate of change is just going to be df over h. And what is this delta f? Well, that's just going to be the height difference here. So this part, and this part is just going to be it's just going to be f of this point minus f of this point. So that's going to be f of x naught plus ha, f of y naught plus hb minus f of x naught y naught over h. So that's the rate of change between 2 points that are arbitrarily far away. But to get the instantaneous rate of change, we can kind of refer back to our definition of derivatives in Calculus 1 with single variable functions. And we can just take the limit as h goes to 0 here. And that will give us the instantaneous rate and thus the directional derivative of u. So we're going to get that du hat of f at x naught y naught, some point x naught y naught, it's going to be the limit as h goes to 0 of this up there, so it's going to be plus ha y naught plus hb minus f of x naught y naught all over h. So that's our definition. Now let's quickly use this to finish the proof of how to calculate this in terms of the dot product. So to begin, we'll consider the function g of h is equal to f of x, y, such that, well, our domain is kind of defined by the line x of h, and this should look familiar, is equal to x naught plus ah, and then y of h is equal to y naught plus bh. Okay, so that's kind of the line where we have our unit vector AB. Okay, and that's kind of the motivation for considering this somewhat arbitrary composition. So now I want you to consider the derivative of h at 0 in 2 ways, and note that it is differentiable by the multivariable chain rule, since we can clearly differentiate this. So note that on one hand, g prime of h at 0, let's just consider it at 0, this is going to be equal to, well, by definition, it's just going to be equal to the limit as h goes to 0 of, well, we're just going to have g of h, because we're going to have 0 plus h, which is just h, minus g of 0 over h. And notice that, well, g of h is by definition this function here with these inputs. So it's just going to be f of x, y, where I'm just too lazy to basically write this out here, minus f of x naught, y naught, all over h, and the limit here, which I'm just abbreviating. And that's by definition the u hat, so the directional derivative with respect to u hat at x naught, y naught. Okay? Of f at x naught, y naught. And now let's evaluate this instead with multivariable chain rule. So, well, if we just take the derivative of this function without setting it equal to 0, well, we're just going to get, now this time I'll write this to be careful. We're just going to get the partial derivative. I'll write it in a nicer way. So I'll just write it as f in the x direction at x naught plus ah. And then, well, it's going to be dx dh, but we note that that is actually just going to be a, and then plus f sub y, y naught of y naught plus bh, and for similar reasoning, we're going to have times b. But now is when we set h equal to 0, so when we set h equal to 0, this just becomes, oh, I forgot to add the second coordinate, whoops. I should have said, I should have actually included the first and second coordinate here, so that's going to be y naught plus bh, and then here in front it should be x naught plus ah. Okay, so in other words, what we have here is that when we let h equal 0, we're basically just going to get, well, f sub x at x naught y naught a plus f sub y at x naught y naught b, which is just the partial derivative of f at x naught y naught dotted with u. So that finishes the video, and I hope you enjoyed, and have a nice day. Goodbye.